Let's talk about finding the slope of a straight line. So we'll talk about the graph of displacement versus time and the v versus time. The equation of a straight line is y equals mx plus b. So here y and x are the variables, x variables, and the variables y variables. This m is the slope. This can be found by rise over run. So if I take 2 points over here and find the rise and the run, so this will be, in this case, delta y. This will be like delta t. So the slope will be delta y over delta t. This is the slope. And here b is the y-intercept. You can look at here. This is the y-intercept. Okay. This concept can be used in the other graph. So this is a plot of displacement versus time. So displacement is plotted along y-axis and time is plotted along x-axis. Okay. So this is a straight line. I take 2 points. So my 1 point is a x2 and time t2, and that point will be x1 t1. Okay, so clearly my rise will be x2 minus x1, and my run will be t2 minus t1. So rise, so slope m equals rise over run. So this will be x2 minus x1 over t2 minus t1. So this is delta x over delta t. So clearly, by definition, delta x over delta t gives you the average velocity, and it will be measured in meter per second. Okay. So this gives the idea that if you find the slope of displacement versus time, this gives you the slope will give you the average v. Okay. The same concept can be used further. In this case, this is a car path, so may not be a good idea to feed a straight line. Idea to fit a straight line. So we have to draw a tangent at a particular point. Say this is the point P. We have to draw a tangent line at point P. This is the tangent line. So as before, we have to find the rise over run. So delta xp over delta xt, that basically gives you the slope at point P, and this is the instantaneous velocity at point P. Similarly, if we consider point Q and we have to draw a tangent line, so delta xq over delta t and delta t for the point Q, that gives you slope at point Q, and this is the same as instantaneous velocity at point Q. So those instantaneous velocities at P and Q may or may not be same. That means that could be different. Let's take another example of graph of V versus T. So in this example, it has three straight lines. So one straight line is AB, second straight line is BC, and third straight line is CD. Okay. So my goal is to find V for the acceleration for each section. Okay. So find slope. First goal is find the slope for straight line AB. Okay. So this will be rise over run. So look at here. There are 2 points A and B. So rise will be, it will be 8 minus 0, and run will be 20 minus 0. So this rise over run in this example is clearly delta V over delta T. That equals 8 over 20. So 8 over 20, if I do little algebra, that gives me 0 0.4, and V is changing V over changing T, so the unit will be meter per second square. So the slope here gives you the acceleration for straight line AB. So this is the straight line. So you can see here the slope of a straight line gives you the acceleration for this section. Okay. Let's find the slope for the section BC. The slope for section BC will be similarly rise over run, rise over run. But here interesting is this, rise will be 0, say 8 minus 8, and run, if I take point A and B, run looks like 40 minus 20. So clearly the acceleration for this section will be 0 meter per second square. Okay, let's go to the section CD. So slope for the section CD will be rise over run again, rise over run. Now the rise will be rise will be, you can see here 40, final position will be so look at here, rise will be 0 minus 8, right? And run will be here. If you look at here, this looks like 47. So 47 minus 40. So roughly 8 over 7, but be careful that is minus. It will be minus 1.14 meter per second square. So this gives you, this is the acceleration for section or the part CD. This is a straight line. Okay. So you can look at here that depending on change in V, acceleration is different. So here, if you look at here, V is increasing. So this is the speeding up case. Right? In section BC, you can look at here, the velocity is constant. So it is the case of constant velocity. So for the constant velocity, clearly acceleration will be 0. Now, if you go to the section CD or the part straight line CD, the V is decreasing. For example, 8, then slowly going down to 5, maybe going to 2, finally it is 0. So this is it is the slowing down case. Okay, so slowing down case, so that minus indicates that it, in this example, is slowing down, it is slowing down. So clearly, if you look at here, speeding up case, this situation, first situation, V is increasing, change in V is positive, and acceleration is also positive. Okay, so in the second situation, acceleration is 0, and third situation, acceleration is minus, is negative. So that's how we can find the acceleration from the graph of v and t. You can use this concept to answer the other questions. So in example 4, instantaneous acceleration, clearly the here the v is plotted along y-axis and time is plotted along x-axis. So this is a curved path, so we cannot fit a straight line. Say we have to choose a one particular point and then draw a tangent line. Draw a tangent line. Then, as before, you have to take 2 points on the tangent line here. That gives you rise, that will give you run. So here, so the difference, say we can find this point and that. So this will be rise over run will be, we can find at this point V2 or V final over V initial or T2 minus T1. In general, we can write delta V over delta T. That gives you here in this example, if I call this point P, that gives you A. This is the instantaneous acceleration at point P. Okay. You can use the previous learned concept for this problem. And similarly, you can use the concept for this problem too.